Hello there, welcome to section 2 of Unit 2, and in this section, we'll be looking at impulse and momentum. Let's go through the objective of this section. At the end of this section, you should be able to define a momentum, state the relationship between impulse and momentum, explain the concept of conservation of momentum, and lastly, define Newton's second law from the concept of what? Momentum. Given a mass m and a velocity v, we can define a momentum mathematically as the product of what? Mass and velocity. And the unit here becomes what? Kilogram meter per second. Let's look at a particle moving in an arbitrary direction, meaning we will have three components for the what? For momentum. That is going to be px, py, and pz. And the formula for the px is going to be what? M times vx, because we are having a constant what? Velocity, and it's only the direction in the velocity that is going to change. So we are going to have py to be also equal to what? M vy. There's a mistake here, there should be an equal to here. Py equals M vy. Likewise, pz will also be equal to what? M vz. Now let's look at the momentum of an n particles. That's an n number of particles. Then, meaning that we are going to have momentum to be equal to p1 plus p2 plus p3 to pn, meaning p1 for a particular number of particles, p2 for particle 2, p3 for particle 3, till we reach a definite number of particles. So the momentum for this series of number of particles becomes n1 v1 plus m2 v2 plus m3 v3 plus to the n say mn to vn. Impulse. We can define impulse as a certain amount of force you apply to a certain amount of time to cause a change in what? Momentum. And mathematically, we can express impulse as force times change in what? T. That's our time. From our previous slides, we know that F is equal to what? ma. That's mass times acceleration. And we know that a2 is what? Acceleration, and is equal to what? Change in this velocity over what? Over time. So we can replace the F that we have here, that's the ma, where we know that our a right now is what? Change in velocity, that's vf minus what? Vi over t. So what I've just written here all represents what? The force, which is going to multiply what? The t that we already have here. So from here, we can just cancel this t out here, this t out here, so that we multiply the m through the f, vf minus what? Vi, so that at the end we will get an expression like m vf minus m vi, which is going to give us what? A final momentum minus the initial momentum. So we can also express impulse as the final momentum minus the initial momentum. Let's look at the relationship between momentum and the second law of motion. We already know that the formula for momentum is equal to what? The product of mass times velocity. Let's find the rate of change of momentum, so that we find dp over dt as what? Dmv over dt. Because let me step back a little, we have p equals mv. We want to find the rate of change, so we differentiate both sides, the p side and the mv side, so that we get this particular expression. I hope you get it. So let's use product rule for this. In product rule in differentiation, we are going to differentiate the two terms that we have here, that is the m and the v. But before we do that, anytime we differentiate, we are differentiating one term, say m, meaning the v here becomes constant, and anytime we are differentiating the one term here, say v, the m here stands out and becomes constant. And that is what we have here. So we first differentiate the v over dt, m stands out, we differentiate m over dt, and what? V stands out. But because m is a constant here, all this term becomes what? 0. So that you get our final answer as the change of rate of momentum to be equal to what? M change of rate of velocity, as we have here. But do you remember that acceleration is always equal to change of rate of velocity over change of rate of what? Of time. Meaning we can represent the whole term that we have here, dv over dt, to be our a, so that at the end dp over dt will be equal to what? Ma. I hope you do recognize this formula, where we derived it at the second law of Newton. Still on momentum, let's look at the relationship between momentum and impulse. In our previous slides, we've discussed or related momentum with the second law of Newton. So, from our momentum formula, we know that change in P over change in T is equal to F. That is also equals to what? ma. We proved this just before this slide. So from here, we can just make the P the subject, so that the change in P becomes what? F change in what? T. So we've moved this particular term and let it attach to what? To the F. I hope you do understand. So from here, we'll be taking it from here at this first expression that we have here. We can integrate both sides here with respect to what? With P here, and we integrate both sides here with respect to what? Change in T. When you do your integration well, because there is a constant here, say 1 here, we are going to get P2 minus what? P1. And because we have another constant here, which is our variable, say F, when you integrate both sides, when you integrate it, we are going to get what? F into bracket change in T, that is what? T2 minus T1. So at the end, after multiplying by F, we can just represent the whole term that we have here to become what? Change in T. So that our F will be multiplied by what? Change in T equals what? P2 minus P1. And I hope you do remember that mathematically we expressed impulse as what? F times change in T. And P2 minus P1 can be our what? Change in momentum. So from here, we can just say that change in momentum is equal to what? Impulse. Where the change in momentum is what? P2 minus P1, or mv2 minus mv1. Collisions. What is a collision? Collision is said to occur when two bodies physically exert relatively strong force against each other, or when the part of one body is changed by the influence of another body. There are two types of collision, which can be what? Elastic and inelastic. So from our table here, we are going to go through the differences between what? The types of collision. 1. For the elastic collision, both momentum and kinetic energy is observed. Likewise, for the inelastic collision, it's only momentum that is conserved, but we don't have kinetic energy being conserved. For the elastic collision, the formation is what? Is temporal. Unlike the inelastic collision, the formation is very permanent. For the elastic collision, mechanical energy is not converted to any form of energy. But for the inelastic collision, because the formation is very permanent, we have other forms of energy being formed. For the elastic collision, colliding bodies separate right after collision. But for the inelastic collision, the body sticks together after collision. So let's look at one-dimensional collision. I hope you do remember some things that we stated in inelastic collisions in our previous slide, like only momentum is conserved and kinetic energy is not conserved, and also stating that the body sticks together right after collision. Here we'll be observing two bodies here, and one is to find if they are all moving together and oppositely collide. And the second one that we look at here is if one is stationary and one is moving to collide. And here we will be comparing the before the collision and after collision. And you know why we do that in our next previous slides, where we will be stating the laws of conservation of motion. So the first one, inelastic collision between two bodies moving in opposite direction. Here our body 1 is is m1 u1, and our body 2 is m2 u2. That is the momentum. And we have after collision our body 1 as m1 and our body 2 as m2. So before the collision, we have to find the summation of before the collision and the summation of after the collision. So before the collision, we are going to get m1 u1, and it's a minus here because the body 2 is moving opposite of body 1, so that we get m2 u2. After collision, they are going to get the same velocity, because in the properties of the inelastic collision, we said it sticks together after collision, and because it has stick together, they are going to all move in the what? Same constant velocity, which is going to be represented by what? By v. So that we have m1 plus m2 all multiplied by what? V. Let's look like inelastic collision between two bodies, but this time around one is stationary and the other one is moving. So you have to take care of the direction in which they all move, depending on the question that we are giving at. So you have m1, before the collision you have m1 u1 plus m2 and 0 because it's stationary and it has no velocity. So you get what? 0 here, to be equal to m1 plus m2 all multiplied by what? The same velocity that they are having as v. Let's look at the third situation here. And here we have an inelastic collision between two bodies moving in the same direction. So before collision is always equal to what? After collision. So that we get our m1 u1 minus m2 u2 to be equal to what? m1 plus m2 all multiplied by the what? The same velocity after collision, that's v. With the elastic collision, we explained that elastic collision has both momentum and kinetic energy what observed, and also after collision the bodies doesn't stick together. So let's look at a situation here where we have two bodies moving in the what? Same direction. We know that before collision is always equal to what? After collision. So we are going to get our mathematical expression as m1 u1 plus m2 u2 to be equal to what? m1 v1 plus m2 v2. And this is for the momentum conversation. Then we have for the kinetic to be what? 1 over 2 m1 u1 squared plus 1 over 2 m2 u2 squared to be equal to the after collision, that's 1 over 2 m1 v1 squared plus 1 over 2 m2 v2 squared. Let's look at the two-dimension elastic collision. And here we will be considering along the x-axis and also along the what? Y-axis. So for elastic collision where we have two bodies, one is stationary, say the m2 is stationary, and the m1 is what? Is moving. Because we have the m2 to be stationary, the velocity for the m2 will be what? Will be 0. But here we have the velocity of the m1 to be represented as v1 I, right? So for along the x-axis, we are going to get what? m1 v1 I for this particular body, right? So that the m2, right now we have the velocity to be equal to 0. So this one will be what? Will be 0. But this time around, after collision, they are moving at a particular angle. So the velocity, the momentum after collision will be m1 v1 f, that's the final velocity, cos theta 1, which is for this particular expression. And the down part, m2, there's a mistake here, sorry, m2 v2, right, v2f cos theta squared. Let's look at the y direction, along the y direction. Along the y direction, because the object, the body was moving on only the x axis, we are just going to get the before collision all to be what? To be 0. So that the after collision will be m1 v1f plus m2 v2f sine theta squared. Finally, for elastic collision, we have both momentum and kinetic energy conserved. So we look at the kinetic energy, and for the kinetic energy in two dimensions, we have 1 over 2 m1 v1 squared equals 1 over 2 m1 v1 squared plus 1 over 2 m2 v2 squared.